Hello everyone and welcome back. In this video we're going to explore AC, that's alternating current circuits. This is in contrast to DC circuits, that's direct current circuits, because in a DC circuit the current flows only in one direction. So if you have a battery that's pushing the current in one direction, you expect the current to flow only in that one direction. Whereas in an AC circuit, that's an alternating current circuit, the current's going to be pushed backwards and forwards, backwards and forwards. So imagine water flowing in one direction and immediately flowing back in the other direction. It's like chug-a-chew, 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 back and forth, back and forth. So you might ask yourself, what's going to cause current to move back and forth? And it goes back to what we talked about with Faraday's law of induction. In Faraday's law of induction, we said that if we change the magnetic flux, we're going to produce an EMF that opposes that change. Okay? So for example, if we increase the magnetic flux, that's going to create an EMF in one direction. If we decrease the magnetic flux through a loop, that could be a solenoid or just a single loop of wire, that's going to change the EMF back in the other direction. So if we change the flux, so if we increase the flux and then decrease the flux, increase the flux and then decrease the flux, then that's going to create an EMF pointing in one direction, pointing back in the other direction, and when the EMF changes direction, naturally the current is going to change direction as well. So you might ask yourself, that sounds really complicated. How could you change the direction of the magnetic flux, increase and decrease? Well, it was Nikola Tesla who had the following idea. Imagine that you had a current carrying wire, so a loop of wire like you see here, and imagine that we are inside a magnetic field. So imagine a gigantic solenoid that's producing a magnetic field, okay? Now, if I rotate this coil of wire like so, notice that the flux through the loop is increasing, right? Goes back to the idea of firing an arrow. Right now, you can't fire an arrow through this loop if you try to fire it straight on. But as it rotates, the amount of field lines that can go through this loop increases, right? So that means that the magnetic flux through the loop increases as it rotates, okay? So now we have an increasing magnetic flux, but as soon as we pass that vertical point, now the magnetic flux starts to decrease, okay? When we go back around, we're now decreasing that flux, and then increasing that flux, decreasing that flux, and now increasing that flux, right? So as it rotates, it naturally is going to experience an increase and a decrease in the flux. And you might notice that the increase and decrease is alternating, right? So we're increasing the flux, and then immediately we start to decrease the flux. We're increasing the flux, and then decreasing the flux, right? So through the natural rotation of that coil, we're experiencing an alternation in the increase in flux and then the subsequent decrease in flux. When we have that increase and decrease in flux, if you go back to Faraday's law, you can simply state that if you rotate a coil, so this represents our coil here, in a B field, the magnetic flux alternates between increasing and decreasing. Okay? So let's say the magnetic flux is increasing. This is going to induce an EMF, and you might call it a back EMF, because it opposes the change that produced it. And that's going to create a current. So if it's a back EMF, we might call it a back current. Whereas when the flux is decreasing, now with a decreasing flux, it's also going to induce an EMF. But because now the direction of the change in flux has switched from increasing to decreasing, now we're going to have an opposite effect. Now we're going to be pushing that EMF forward. So you might call it like a forward EMF, in the sense that it's changed direction at this point. And that is going to create like a forward current. So as this rotates, it's creating a back current, forward current, back current, forward current. And that is happening at the power plant. Now, what kind of power plant could it be? It could be a wind turbine. So when you put a wind turbine in a wind, it's going to start to rotate. Okay? Inside that wind turbine is a coil of wire inside a magnetic field that's creating this backward and forward current, this alternating current. If you have a nuclear power plant, you're going to use a nuclear reaction to generate a lot of heat. That heat's going to boil some water. The water is going to evaporate as steam. The steam is going to turn the turbine, and guess what? At the end of the turbine is one of these, a loop of wire that's turning inside a magnetic field. Same thing with coal plants or natural gas. Anything where you're burning something, you're going to be creating steam, which is going to turn a turbine. So that's all very cool. The next thing that we want to look at is this idea of the voltage. So if the voltage is alternating, what would that look like? Let's draw a graph. So on the vertical axis, let's draw the voltage V, and we know that the voltage is going to alternate from a positive value, so this would be our positive, and a negative, so it's going forward and backwards, right? And it turns out that this function is going to be a sinusoidal function like this. So as the coil spins, it's going to produce voltage in one direction, positive voltage, voltage in the opposite direction, a negative voltage, back and forth, back and forth. This represents the alternating voltage and therefore the alternating current. Now, what we might do is say, okay, it achieves some maximum voltage. Okay, we might call this positive V max, and down here we might call this a negative V max. Is it always going to be at this maximum value? No, right? Through all this time in between the maximum values, it's less than the maximum value, right? So the question is, well, what's the average voltage? What's the average voltage that this circuit's going to produce? So what we do is we look at the absolute value of these voltages. So check this out. I'm going to draw another graph like this where I represent the absolute value of the voltage, okay? And this is a function of time, okay? If I represent the absolute value of the voltage, you're going to see that we start out with this positive voltage that we had before. Okay, that's fine. Then this negative voltage gets reflected, you could say, above the t-axis, and it's going to produce a nice positive voltage. Then we have this voltage here, which is also positive, and then this voltage, again, the absolute value takes anything negative, makes it positive, so this comes up here like this. Okay? This is the magnitude of the voltage. Now, how does this help us? Well, it gives us an idea. It says, look, if this is the maximum value up here, then there's gotta be some average value of that voltage. Okay? And you might say to yourself, well, where is the average value? Well, it's got a special name. Okay? It's called the root mean square voltage. And the root mean square refers to the technique that we would use to calculate this average voltage. It's kind of like the average voltage. So we're going to call it the average voltage. And you see the word mean is right in there in the definition, right? So the way that we calculate the RMS voltage, we call this the RMS voltage, the VRMS, root mean squared, is equal to the maximum voltage divided by the square root of 2. Okay? And that makes sense because the square root of 2 is bigger than 1. So if you take the maximum voltage, this Vmax that you see up here, if you take that Vmax and divide it by a number bigger than 1, you're going to get an RMS value, an average value, that's a little bit less than the maximum value. So this here would represent VRMS. Okay? So when you talk about outlets in your house, and the average, house has a voltage in every outlet of about 120 volts, that is actually the RMS voltage. So when you say the household outlet has a voltage of 120 volts, that's actually VRMS. VRMS, remember RMS means root mean squared, is equal to 120 volts. Now, a worthwhile exercise is to calculate the maximum voltage in your house. Well, you could do that very easily by solving for this Vmax. Take your VRMS times square root of 2, and you can solve for Vmax. All right. So when we talk about RMS, we're talking about the root mean squared. That's the average voltage. It's going to be very natural for us when we study circuits to not just worry about the voltage, but to also worry about the current. Okay. Now, from Ohm's law, we can state that V equals IR, always true. But if this is the RMS voltage, we can replace this with VRMS and say that's going to produce an RMS current, an average current, I RMS. Okay? And so you could use this equation here, Ohm's law, to solve for the RMS current. That would be the average current flowing in the circuit. All right. Good deal. Let's move ahead. Another thing that we can study is power. So power, we learned, is current times voltage. We also studied how power can be represented I squared R, or as V squared over R, right? So if we're looking at the RMS voltage, remember that's like an average voltage. If we wanted to calculate power, we'd be calculating the average power. So you may see a problem where it says calculate the average power, and P_av would be these equations here. We could write I RMS, V RMS, or we could say it's equal to I RMS squared over R, or pardon me, times R, or we could say this is equal to V RMS squared over R. That's kind of, let me write this a little bit. V RMS squared over R, right? Following the same pattern. Okay, good deal. Let's move ahead. The next thing that we want to study is capacitors in AC circuits. Okay. Let's talk about capacitors in AC circuits. The way that we draw a capacitor in an AC circuit is as follows. We're going to start with an AC source. Now check this out. This is kind of cool. So we draw an AC source like this. Start with a circle and draw a little sine wave. And the little sine wave harkens back to our diagram of the voltage, right? Remember that little sine wave that we saw with the voltage? That little sine wave that you see in there is representative of the voltage changing directions, positive, negative, positive, negative. And you see that in there in the symbol. Okay? So now we're going to draw a standard circuit. So with our AC source, and this is going to have a VRMS, so if you want to label VRMS, we're going to say, okay, let's put a capacitor in this circuit. Like that. Okay? And let's talk about how you would charge this capacitor. Ordinarily, if you hooked up a battery to the capacitor, time would go by, the charge would develop on the plates, and everything would be fine. But because the current is changing directions constantly in an AC circuit, the capacitor doesn't have enough time to develop a full charge. So what we're going to say here is charging a capacitor takes time. That's one of the things we learn about charging capacitors. And as the current changes direction, the capacitor cannot get fully charged. And the capacitor will actually I'm going to put this in quotes here, it will actually resist the flow of current because the charge on the capacitor blocks, or you could say impedes, the flow of charge. Okay? So we have to think about capacitors as kind of opposing or blocking the flow of current in a circuit. Now, the more charge the capacitor gets, the less current can flow because the capacitor gets fully charged, fully saturated with charge. So what we're going to take a look at here is this relationship between the oscillation of this current, right? If you look back at this graph, this is an oscillation. You see the voltage oscillating in simple harmonic motion. That means that the current is also oscillating in simple harmonic motion. So what that means is that when we look at this oscillation, we have to look at the frequency of the oscillation. And let's take a moment to look at that frequency. You may remember when we studied oscillations, we said that the frequency of an oscillation is equal to 1 over the oscillation period. That's the time for a single oscillation, right? And from this, let's go a little bit further. Let's consider that if something is rotating, right? If you have a turbine, a wind turbine, a hydroelectric turbine, a nuclear power plant turbine, that turbine is going to have an omega. Now you might remember omega is the angular velocity, and omega is defined as a change in theta over a change in time. And if it's oscillating, if it's rotating at a constant rate, we can say, okay, it's going a full rotation, that's going to be 2 pi radians over a certain amount of time. And that time we call the rotational period, or the oscillation period, capital T. Now notice, capital T in the frequency equation, capital T in the omega equation. So that means we can make a substitution here to find a relationship between omega and the frequency f. So let's do that. Let's solve this for t. If we solve this for t, so solve for t, we're going to get t equals 2 pi over omega. And if we substitute this into f equals 1 over t, that's going to give us f equals 1 over this expression right here. So 2 pi over omega. And if you divide 1 by a fraction, you get the reciprocal of that fraction. So the omega jumps into the numerator, and you've got the 2 pi in the denominator. And if you solve this for omega, you're going to get, let's see, I'm going to move this up a little bit here so we can see this a little bit better. We're going to get omega equals 2 pi f. And please put a rectangle around this and star it, because this is how you calculate the angular velocity omega from the frequency f, and vice versa. Okay, very important equation right there. So now you might be asking yourself, well, in an average household outlet, like the 120 volt outlet that you plug your laptop into, what is the frequency? So in a home outlet, the frequency is 60 hertz. So when you plug something into the wall, the frequency of that alternating current is changing 60 times a second. That means 60 times in a second, the current is changing from backwards to forwards. So imagine backward, forward, backward, forward, backward, forward, backward, forward. 60 times a second. That is the frequency of that oscillation. All right, so let's keep moving forward. Because we claimed that charging a capacitor takes time, and as the current changes direction, the capacitor can't get fully charged, and because we claimed that the capacitor resists the flow of current, I think there should be an S here, capacitor resists the flow of current because the charging capacitor impedes the flow of charge. Because all of this, we're going to make a fantastic claim here. You ready? We're going to claim that the capacitor offers its own resistance. We call that the capacitive reactance. We can't call it resistance because resistance is specifically for resistors. Okay? The capacitive reactance is X sub C. Okay? X sub C. And the definition of the capacitive reactance is this. It is a resistance. Even though we can't call it a resistance, because the word resistance is reserved for resistors, it is a resistance. And I'm putting quotes. It's a resistance provided by a capacitor in an AC circuit. Now, if it's a resistance, in reality it's a reactance because it's reacting to the change in the current, what do you think the unit is? The unit in the SI system is the ohm. And that's the best clue that you have that this reactance acts like a resistance. Okay? It's called a reactance because it's a different concept, it's a different physical quantity than resistance in a resistor, but it provides the same function. It impedes or resists the flow of current, and the unit therefore is the ohm. Okay? That's pretty cool. All right, now the way that we calculate the capacitive reactance is as follows. All right. The capacitive reactance, X sub C, is equal to 1 over omega. Remember, omega was the angular velocity of the rotating coil times the capacitance C. Okay? Let's take a moment here and analyze how this quantity changes as omega changes. Let's start with letting omega approach infinity. Okay? As omega goes to infinity, so what are we talking about here? We're talking about something spinning so fast that we're letting that angular velocity approach infinity. Okay? What happens to XC? What happens to capacitive reactance? Well, as omega gets very big, ask yourself, where is omega? It's in the denominator, right? If the denominator gets very, very large, if you take 1 over a very, very large number, that's going to get closer and closer to 0. So XC is going to approach 0. Okay? What about as omega approaches 0? What if it's really slow? What if it's barely rotating at all? Well then, if this gets very, very small, then 1 over a very, very small number approaches infinity. The capacitive reactance is going to approach infinity. Now, how do we make sense of this? If it spins very, very fast, then there's really no time. There's no time for charge to accumulate. If it's spinning very, very fast, then there's no time for that charge to collect because the charge is going one way, it's going back the other way. There's no time for the charge to collect on the plates. And with no time for the charge to collect, that reactance is going to be very, very small because the reactance is dependent on the charge. If there's no charge on the plates, then there's very little reactance. Okay? What if it's rotating very slowly? If it's rotating very slowly, then the reactance is going to be very, very high. How does that make sense? Well, if it's rotating slowly, then there's plenty of time for the charge to accumulate on the plates. So charge accumulates. And when charge accumulates, that's going to provide reactance. It's going to be more opposition, more reactance. All right, please put a rectangle around this quantity here and star it because the capacitive reactance is a very important quantity that we have to calculate in this topic. All right. Good deal. Let's move ahead. And let's talk about our next subject, which is RC circuits. Now, an RC circuit is special because it has both a resistor and a capacitor, and that's what the RC stands for, right? It's a resistor and a capacitor. So let's draw an AC circuit with a resistor and a capacitor. We'll draw it like this. We'll start with our AC source, and again, there's our little sine wave to indicate that it's an AC source. It's going to be rotating at an angular speed omega, so we're going to label the omega on that AC source. Then we're going to have a resistance from the resistor. I'm going to label that R. And then we're going to have a capacitor of capacitance C in our RC circuit. All right. Now, let's talk about what we have here. We've got a resistor. And what does it do? It provides resistance. That's what a resistor does, right? What about the capacitor? Capacitor, it's going to provide reactance. So it provides reactance. All right? So if the resistor provides resistance and the capacitor provides reactance, what do they both provide? So together, in a circuit, they both provide what's called impedance. And if you think about it, in the English language, these three words kind of mean similar things, right? Resistance is like an opposition. The reactance is like an opposition. I'm reacting, pushing back. The impedance, to impede something, is to slow something down, right? That's an opposition as well. So these all kind of mean, in the English language, a very similar thing. So together, the resistor and the capacitor provide impedance. Okay? Now, what is impedance? Impedance, let's define this. So I'm gonna move this kind of up here like this. I'm going to bring this in here. Okay, so impedance is the quantity Z. We haven't used Z yet in our study of physics. This is kind of cool. The impedance Z is a measure of total opposition to current. And what do you think the unit is going to be? The unit is going to be the ohm, just like resistance and just like reactance. All right, good deal. So how do you calculate the impedance in an RC circuit? So the impedance in an RC circuit. Here we go. Z is equal to the square root of R squared plus XC squared. So looking back at the diagram, if you were to take the resistance and square it, the capacitive reactance and square it, and then sum those and take the square root, you would get the impedance. All right, so that's pretty cool. Let's move ahead. The next thing that we're going to study is inductors in AC circuits. Okay. What is an inductor? So recall that an inductor is a coil of wire. We're talking a solenoid. That's it. That's all it is. So let's consider that by Faraday's law of induction, you may recall that the magnitude of the EMF is equal to the number of coils in the circuit, or in the coil, times the magnitude of the change in magnetic flux divided by the change in time. So what this means is if you have changing magnetic flux, it's going to produce an EMF. And we talked about how as the current changes, that's going to produce its own magnetic field inside the coil. Okay? So let's say you're increasing the current forward. Okay? So here we go. If I were to draw an inductor, here's an inductor, right? It's just a coil of wire. That's all it is. Okay? And if I were to have a current flowing this way through the inductor, okay? Current flows this way. I'm going to induce a back EMF because the magnetic flux through this coil is going to be changing. So as I increases, the magnetic field inside the coil is going to be increasing as well. And if the magnetic field increases, the magnetic flux, which is equal to BA, is also going to be increasing. And if the flux is changing, anytime you have a changing flux, you have a new EMF that's being generated. So the back EMF is going to be pointing in the other direction as the current increases in this direction. But then when the current starts going back the other way, the EMF is going to be generated in the other direction. So this inductor is going to be experiencing this back EMF, which is pushing back and forth and back and forth. Because it's a back EMF, it's always opposing the EMF that's trying to push the current forward. And that means it's going to provide its own little resistance. Okay? And a nice way to summarize this is like this. A change in current in a solenoid produces a back EMF, which pushes back and thus resists. Remember, pushing back means to resist. It's going to push back on the current, which is going to resist the current, and it's going to resist the flow. Okay? That's going to produce its own, not a resistance, it's going to produce a reactance. Okay? Not a capacitive reactance, it's going to produce what's called an inductive reactance. Okay? So let's take a look at that. We're going to have here what's known as an inductive reactance. Now you have probably figured out that the symbol for reactance is X, right? And whereas the capacitive reactance was X sub C, this is an inductive reactance, so it's going to be X sub L, because the symbol that we use for inductance is L. So this is X sub L, and what it is an opposition. It's an opposition provided by the back EMF in a solenoid. All right, now how do you calculate the inductive reactance? X sub L is equal to omega L. Very, very simple. So please star this. And let's explore a little bit what's going on in this equation. Let's let omega get very large. So as omega approaches infinity, okay, what's going to happen to X sub L? What's going to happen to the inductive reactance? X sub L is going to also approach infinity, because you see this direct proportionality between omega and the inductive reactance. Now what that means is, if this is spinning really fast, so if something is spinning so fast that it's going back and forth very, very quickly, that back and forth, if you think about Faraday's law of induction, it's the change in flux with respect to time. So if it's changing back and forth very, very quickly, because it's rotating very, very quickly, then that means that you're going to have an astronomical amount of EMF, which is going to push back very strongly and produce a very large inductive reactance. Okay? What about as omega approaches 0? Well, direct proportionality dictates that x sub L will also approach 0. What does that mean? If something is rotating very slowly, then that change with respect to time is also very slow. It's very sluggish, okay? And if it's sluggish, if it's slow, you're not going to get any of this delta phi, delta t, right? Because there's no change that's happening very quickly. It's happening very slowly. And a slow change in flux with respect to time is going to mean a very small back EMF, which will mean a very small inductive reactance. Okay? So that's very, very interesting. And the unit, of course, is going to be the ohm. All right, very good. Let's move forward. What we want to study now is what happens when you put a resistor and an inductor together in a circuit. That's called an RL circuit. So let's draw this out. Let's start with our AC source. Here's our AC source with angular velocity omega. We're going to put a resistor in our circuit. This is R for resistor. And then we're going to put an inductor. Now when you draw an inductor, you want to draw basically a coil. And the way that people typically draw a coil is they start here and they go loop around like this. Okay, this represents a coil of wire. Kind of looks like a spring. And this has an inductance L. Okay? Now, what we're going to look at here is if there's a resistor and there's an inductor, and this has resistance and this has reactance, then together, what do you think they have? If it follows the same pattern as an RC circuit, it's going to have what's known as an impedance. So let's look at the impedance in an RL circuit. The impedance in an RL circuit is going to be Z equals the square root of R squared plus the inductive reactance, so X sub L squared. Same exact pattern that we saw for the capacitor. All right, please put a rectangle around this, and let's star this. And I want to take a moment to really emphasize that because the unit for all of these topics, all these quantities, the impedance, the reactance, the resistance, because they all have the same unit of ohm, they all behave like resistors. And because they behave like resistors, you really have to keep this equation in mind. You have to remember Ohm's law. Ohm's law can be expressed in terms of the typical V equals IR, but if we replace this resistance with an impedance, we can also express this equation as V equals IZ. Okay? This is our impedance. And it acts like a resistance. It acts like resistance. And it's very important for us to remember that this equation is the one that we need. If they give us a whole bunch of quantities, let's say they give us omega, they give us R, they give us L, we might have to calculate the inductive reactance. We might have to plug that into the equation for the impedance. to calculate Z. And from there, we might need to solve for the current by using this equation right here. So to solve these problems, you really have to pull together all of the givens, pull together all of the equations, and piece by piece solve the problem for the quantity that's requested. Okay? Often, the current is what you're looking for. So this is a very, very important, very helpful equation. Let's move ahead and let's go forward to the last type of circuit that we have to consider in this video. The last circuit is going to be called an RLC circuit. And I bet that you can guess what's in an RLC circuit. R for resistor, L for the inductor, and C for the capacitor. How do we draw an RLC circuit? Like this. We start with our AC source with a little sine wave inside the AC source with an angular velocity omega. We're going to draw a resistor, label it R. We're going to draw an inductor. Here's our inductor. Label it L. And then finally, we're going to draw a capacitor. And it's going to have a capacitance C. Now finally, I can get to some applications, because so far you're like, what on earth are the applications of this? Finally, let's talk applications. If you've ever flown on an airplane before, you went through a metal detector. If you went through a metal detector, you walked through an RLC circuit. The RLC circuit, as we're going to see coming up, is going to look for the capacitive reactance. It's going to look at the inductive reactance. And if there's metal inside the circuit, the magnetic field is going to adjust and change to the point where you might have balance between the inductive reactance and the capacitive reactance. So applications would be metal detectors. Another application, if you ever listen to the radio. Transistor radios use RLC circuits to generate resonance, which picks up the frequencies of the electromagnetic waves that you get from radio. So there are some very fun little applications for RLC circuits. And let's take a moment and take a look at how we calculate the impedance. Okay? So if we have an omega angular velocity, an R resistance, L for inductance, and C for capacitance, the impedance for an RLC circuit looks like this. Z is the impedance, and it's going to equal the square root of R squared plus, in parentheses, we're going to have the inductive reactance X sub L minus the capacitive reactance X sub C, close parentheses, squared. So it looks a lot like the other equations for impedance, but now we've got both the capacitive reactance and the inductive reactance together. Now the fact that these are being subtracted indicates that they're in different directions. So X sub L and X sub C are opposite. To one another. And that comes from the fact that X sub L is based on a back EMF. From Lenz's law, the EMF is always generated in opposition to the change that provided it. So this will always be in opposition to the current. So this is how we calculate the impedance for an RLC circuit. So in this type of circuit, you might have to calculate the inductive reactance, followed by the capacitive reactance, and then hopefully you're given the resistance, put it all together, and you can get the impedance for that circuit. Again, once you have the impedance, you really want to jump back and use Ohm's law. Because once you have this Z, you can solve for anything else that you need in this circuit. All right, so now we have the impedance. The unit, of course, is still the ohm, which is cool. And I want to take a moment here and just take a look at the fact that if you were to take either the inductor or the capacitor out of this equation, it's going to collapse back to the equation that you had either for the RC or the RL circuit. So take a look at what I mean. If you were to take away this inductive reactance, let's say there was no inductive reactance here, then you would just have this negative XC squared. A negative squared is just a positive, and so you would really just have R squared plus XC squared. Well, guess what? That's exactly what we had for our RC circuit. So if we go back to our RC circuit right here, if we take away this X sub L, then we're going to get back R squared plus XC squared. Likewise, if we take away the X sub C, and that's gone, we're just going to have R squared plus XL squared, which is exactly what we had for the impedance in an RL circuit, which we saw back over here. There we go. Okay, so just to go back and forth, this was the RC circuit impedance, this was the RL circuit impedance, and as you can see, they all go back to this main equation. So this is really the only equation you really need to memorize or to know for impedance, because it incorporates both the inductive reactance and the capacitive reactance together. All right, very good. Let's take a moment here and let's analyze what happens if we take this equation and we look at large and small frequencies. So check this out. Let's title this section Large and Small Frequencies. Okay? What would happen if omega approached infinity? If omega approaches infinity, let's look at what happens to the inductive reactance first. So the inductive reactance is omega L, and if omega goes to infinity and L is fixed, then that means that the inductive reactance goes to infinity as well. So this will approach infinity. What about the capacitive reactance? The capacitive reactance is 1 over omega C. If omega goes to infinity, then this fraction is going to go to 0. And what that means is this XC is going to behave as if it has absolutely no reactance at all. So this will act like an ideal wire. If it has no reactance or no resistance, then it's going to behave like it has no opposition at all. It's going to act like an ideal wire. Whereas if the reactance goes to infinity, then that means that it's like you basically don't allow current to flow at all. So there will be no current in that branch of the circuit. So what are the applications of this? Imagine that we had a circuit that looked like this. We've got our AC source, and we're going to have in this circuit an inductor, L, followed by a resistor, we'll call this R1, going back to the AC source, and then through a different branch, let's have a capacitor, C, and a resistor, R2. Okay? If omega goes to infinity, this inductive reactance is going to approach infinity. So that means that in a new diagram, if the inductor has infinite reactance, that means current can't flow through it at all. So that's going to look like this. Here's our AC source. If current can't flow at all, it's like there's a break in the circuit. No current can flow whatsoever. So that break there means it's an open branch. No current can flow. Whereas if the capacitive reactance approaches 0, that means it's going to act like an ideal wire. It's like there's nothing there at all. And we're going to have this resistor here, R2. So the current in this circuit, the RMS, remember RMS is root mean squared. If the RMS current can be calculated, it would be based on the VRMS divided by what? If no current can flow, this might look like a parallel circuit, but it's not, because no current can flow through this branch of the circuit. That means this is behaving like a series circuit, where the only resistor that's receiving any current at all is R2. So current is voltage divided by resistance, Ohm's law. So the current will be the RMS voltage divided by R2. What if we now look at the opposite? What if omega is not approaching infinity? What if omega is approaching 0? So if omega approaches 0, let's look at the inductive reactance, which is omega L. That is going to be equal to 0, right? If omega goes to 0, then the inductive reactance also goes to 0. What about the capacitive reactance? If it's 1 over omega C, if omega goes to 0, if the denominator gets very, very small, then the overall fraction will get very, very large. This is going to approach infinity, right? So if we reconsider the original diagram in which we had the AC source, and we had our inductor L, and we had our R1, and we had our capacitor C, and we had our R2, we might ask ourselves, at a very, very small omega, what would the new circuit look like? Well, let's draw it. The very, very small omega is going to produce 0 reactance in the inductor. So that means that current will be able to flow very easily like it's an ideal wire. So current will flow perfectly through that inductor. And we're going to have only R1 opposing that current. Whereas if we have a very, very small omega, the capacitive reactance is going to be very large. So that means that no current will be able to flow across the capacitor. And that means that no current is going to get to this R2, which means that the RMS current is going to be the RMS voltage divided by this R1. All right? So very, very important to think about the limits of omega approaching infinity or omega approaching 0. All right, and there is one more topic for us to study. And that topic is going to be what's known as resonance. And this is a very, very popular topic in college physics. Now, you might recognize the word resonance. Ooh, I already have a paper for this. You might recognize the word resonance because we studied this word when we studied oscillations and when we studied waves. Okay? Now, the way to think about resonance is in terms of this vision that we had earlier of an RLC circuit. Okay? In the RLC circuit, the inductor and the capacitor both provided reactances, but they were in opposite directions. And that was evidenced by the impedance for an RLC circuit, right? That negative between XL and XC indicated that XL and XC are in opposite directions. So rather than adding up and stacking together, they oppose each other, they try to cancel each other out. Well, resonance asks this question. If XC and XL are in opposite directions, if that's true, what would happen if the capacitive reactance and the inductive reactance are equal? If XC and XL are equal, what would that mean? That would mean that the reactances balance each other out. So one reactance is pushing one way, one reactance is pushing the other way. They're going to basically cancel each other out. And we think about this as like an oscillation. So if you think about a mass on a spring that's oscillating back and forth, there's two forces that are pushing back and forth on this mass, forward, backward, right? And those two forces kind of balance out until it oscillates back and forth in resonance, okay? Now, if they're equal, what we can say is that the current is, quote, oscillating back and forth, okay? And it oscillates at what's called a natural frequency. So the current is oscillating back and forth at a natural frequency omega naught. So this omega naught is very special. This is the frequency at which, I should say the angular frequency at which XL equals XC. Okay? So let's take this opportunity to look at the conditions for resonance. The condition for resonance is simply that the inductive reactance equals the capacitive reactance. They're going to balance each other out. Now, the inductive reactance we learned was omega L, and the capacitive reactance we learned was 1 over omega C, and this is the natural frequency omega naught. And if we wanted to solve for omega naught, we would use standard techniques. So maybe we would cross multiply. So this is like omega naught L over 1, so cross multiplying gives you omega naught squared times LC equals 1 times 1 is 1. So that gives you omega naught squared equals 1 over LC, or you could simply write omega naught is equal to the square root of 1 over LC, or omega naught is equal to square root of 1 is 1 over the square root of LC. So please put this in a rectangle, star it. And so this represents the natural frequency at which we're going to see resonance in this circuit, where the two reactances are going to basically cancel each other out. And so in such a problem, you might have to calculate the natural frequency using the inductance and the capacitance. And don't forget that this is an omega. That means it's an angular velocity. Earlier in this video, we derived the following equation. So please recall that omega is equal to 2 pi f. So the angular frequency, the angular velocity is 2 pi times the frequency f. And this is an omega naught, and that's going to be the equation that you would use for omega naught. So sometimes you have to go back and forth between these two equations, and that would allow you to solve any problem that has resonance. And that covers all of the topics we need to study for alternating current. Good luck with your exercises, and please ask questions in the comments if I can provide any clarification. Thank you very much.